breaking news. A strange new object has been spotted, and now we have fresh, high-resolution images that are raising more questions than answers. Earlier today, the Virtual Telescope Project released striking photographs of the interstellar comet known as 3I Atlas. And in those frames, we see features that challenge what we thought we knew about visitors from beyond our solar system. What was discovered? An icy body barreling through our neighborhood of space, arriving from the depths of the Milky Way. It was first identified on 1st of July 2025 by the Atlas Survey Telescope in Chile. But what we are now seeing, a tail that's growing, a coma of intense carbon dioxide gas, a hyperbolic trajectory implying it did not originate in our solar system, and images captured by ground and space-based observatories. Very unusual, very strange. In fact, only 2 interstellar objects had ever been confirmed before this. 1I Oumuamua in 2017 and 2I Borisov in 2019. Agencies around the world, from NASA to ESA, from the European Southern Observatory in Chile to the Lowell Observatory in the US, are tracking it. And now the Virtual Telescope Project has released the newest image sets, sparking fresh scrutiny, debate, and wonder. Today, we're going to dig into what these images show, how they compare with our expectations, what makes this object so different, and whether this is just an extraordinary natural event, or something far stranger. Before we go on, if you're fascinated by interstellar objects, comets, cosmic mysteries, hit the like button, subscribe for more, and drop a comment below telling us where you're watching from. Because this story isn't just about one object in space. It's about how our understanding of the universe is changing right now. In case you're not familiar, 3I Atlas, also designated C2025N1, is the 3rd confirmed interstellar object ever observed passing through our solar system. It was discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS telescope, in Rio Hurtado, Chile, on 1st July 2025. From the outset, astronomers noticed that its trajectory was hyperbolic, meaning it's unbound to the sun and came from outside the solar system. It's been observed by many institutions, ground-based observatories like the European Southern Observatory, ESO, Very Large Telescope, the Hubble Space Telescope, the James Webb Space Telescope, JWST, as well as amateur observatories and the Virtual Telescope Project itself. So this isn't just any comet passing by, it's a visitor from beyond our solar system, arriving in our cosmic backyard. Now, what's new? The Virtual Telescope Project recently released fresh images of 3I Atlas, showing unprecedented detail of its coma, the cloud of gas and dust surrounding the nucleus, and its tail. These images show a coma with significant carbon dioxide content detected by the JWST and the SphereX mission. A tail that is evolving rapidly. Ground-based observations from the Gemini South Telescope, Chile, captured tail lengths of around 50 arcseconds, translating into about 100,000 kilometers of debris. The object moving through constellations Sagittarius, Ophiuchus, Scorpius, Libra, as it approaches perihelion and then recedes. What makes these images important is the level of detail. The Virtual Telescope Project's time-lapses and color filter composites allow scientists to study the coma's shape, nucleus activity, and dust tail dynamics live and in real time. In short, we have better data, sharper imagery, more wavelengths, and that means more questions. Imagine standing in front of a 3-dimensional solar system map rendered by software such as Stellarium or Sky Safari. You see the sun at the center, planets orbiting, then out of the ecliptic plane, an object on a hyperbolic track plunging inwards from the direction of the Milky Way's disk, passing closest approach to the sun on 29th of October 2025. Its inbound vector is from near the constellation Sagittarius, angled steeply relative to the ecliptic, which is unusual for most comets of our solar system. Now zoom in. The Virtual Telescope's images show a fuzzy coma of gas and dust, with a sun-facing plume and an anti-solar tail streaming behind. The tail seems broader, more diffuse than typical. The coma is larger with carbon dioxide-rich gas detected. The nucleus size is uncertain, but perhaps kilometers across. So what you're actually seeing, a wanderer from another star system, glowing faintly, streaming material into space, and being observed as it sweeps past the sun. Usually, comets we see belong to our own solar system. They typically have elliptical orbits bound to the sun, formed 4.5 billion years ago with us. Their chemical compositions are relatively well studied, but 3I Atlas is different. For example, the CO2 to H2O ratio, carbon dioxide to water, in its coma is unusually high, one of the highest ever recorded for a comet. It has a hyperbolic trajectory, meaning it is not bound to the sun, unlike typical comets. It may be older than any comet we've seen before. Some statistical methods suggest it could be twice or even 3 times as old as our solar system comets. Its tail structure, dust ejection rates, coma size, and morphology are all slightly outside the norms seen for familiar comets. What surprised many people is that despite coming from the deep interstellar milieu, its behavior appears in some ways normal, outgassing, tail formation, yet in other ways anomalous, chemistry, trajectory. Let's walk through the key dates we already know. 1st July 2025, discovery of 3I Atlas by the Atlas Survey Telescope in Chile. TAGO July 2025, the Virtual Telescope project captured initial images of the object and made them publicly available. 9th of October 2025, perihelion, closest point to the Sun, for 3I Atlas. Mid-December 2025, closest approach to Earth, though still safely distant. August 6th as soon as 2025, observation by JWST using near-infrared spectrograph instrument. These dates frame our investigation. From discovery to solar encounter to Earth transit and beyond, several major observatories around the globe are focused on this object. The Very Large Telescope, VLT in Chile, ESO, captured a time-lapse with its FORS-2 instrument on 3rd of July 2025. The Hubble Space Telescope captured high-resolution imagery on 21st July 2025. The James Webb Space Telescope made early infrared observations on 6th of August 2025. The Virtual Telescope Project, Italy Remote Robotic Telescopes, was live-streaming the object on 3rd July 2025. The Virtual Telescope Project 2.0 amateur and professional collaborations globally, coordinated via the Virtual Telescope's Shadow the Scientist initiative, helped track the tail growth in August and September. In other words, this is a global effort, many instruments pointing in unison, building data across wavelengths. What caught the attention of astronomers and scientists are several features that don't match normal expectations. For example, the CO2-rich coma with a relative paucity of carbon monoxide, suggesting thermal history unlike typical long-period solar system comets. The hyperbolic inbound and outbound trajectory clearly identifying the object as interstellar. The tail structure that seems larger and more quickly evolving than many comets observed at similar distances. The fact that despite its interstellar origin, it appears to behave in some respects like solar system comets, developing coma, tail, outgassing. This dual nature is intriguing. Its age estimate, possibly older than any comet we've seen, which raises questions about what it encountered and how it survived in interstellar space. In other words, it looks familiar, and yet in many ways it is not. Meanwhile, solar activity continues. The sun is active, solar wind is strong, the heliosphere is dynamic. As 3I Atlas plunges through the inner solar system, the interaction between solar radiation, the solar wind, and the comet's volatile ices becomes ever more intense. What does that mean? The near-sun environment is harsher than outer regions, so volatiles sublimate faster. Tail formation accelerates. Dust and gas is stripped away with greater force. Interestingly, this comet may be giving us a natural experiment. How does an object formed elsewhere behave under our sun's glare? Are its volatiles different? Is its dust different? Not just chemically, but physically, the size of grains, the cohesion, the rate of ejection. What surprised many people is that some of the ejection appears to mimic solar system comets, reinforcing the idea that comets anywhere might share broad behaviors. While some details diverge, chemical ratios, tail morphology. This leads to another question. Are we seeing a typical interstellar comet or a unique outlier? And what does that tell us about other star systems and the building blocks of planets beyond our own? Another important block, the quality of these new images and access for worldwide scientists and amateurs. The Virtual Telescope project made its live stream available on 3rd July 2025, inviting public participation. The challenge remains. Because the object is faint and in dense star fields, particularly early on in Sagittarius near the galactic center background, observational clarity was limited. Nevertheless, what we now have, multi-wavelength imagery, visible, infrared, time-lapse sequences, multiple observatory crosschecks. Each dataset adds clarity and raises new questions. The answer still lies in the vastness of the stars. But with increasingly better tools, we're peeling back layers of the unknown. Here's where things get exciting. This object will continue to recede after perihelion, 29 October 2025, but will remain observable into December and beyond. Changes in tail length and morphology as solar heating intensifies near perihelion. Further spectroscopy, especially ultraviolet, to refine composition, water, CO2, CO, nitriles, metals. Possible fragmentation events if the nucleus becomes unstable. We have precedents, e.g. 2I Borisov, coordinated observations from space-based and ground-based telescopes, including those in both hemispheres' public outreach. Amateur astronomers may capture images, join live streams, share data. In short, this is not just a snapshot. It's an evolving story, an interstellar visitor on a brief but meaningful pass through our system. What does all this mean? If this object is indeed older, formed in another star system, and traveling here now, then it's a messenger from afar. It carries material from beyond our solar neighborhood. That has enormous scientific weight. Traditionally, scientists believed that interstellar visitors would be rare, faint, and behave loosely like our comets. But 3I Atlas is offering a new twist. Yes, some behaviors resemble known comets, but others diverge substantially. In other words, if we only studied comets in our solar system, we might be missing part of the picture. Objects like this expand our understanding of planetary formation, of volatile evolution in different environments, and of the broader architecture of other star systems. Some scientists even wonder whether studying such objects may yield clues to the very building blocks of life, or the transfer of materials across star systems, panspermia theories, though that remains speculative. The most mysterious thing is how an object formed in another system, perhaps billions of years ago, survived the interstellar journey and still arrives intact enough for us to study. It's like looking at a time capsule from another era, another star, now passing by us. Could it be that the universe sends us visitors more often than we think? We just haven't detected them? That leads to another question. Have we only scratched the surface of interstellar object studies? The answer still lies in the vastness of the stars. Current status, as we speak. Right now, as we speak, 3I Atlas is receding from the Sun and moving away from Earth, yet still visible via telescopes with sufficiently large apertures. Data is streaming in from instruments like JWST, Hubble, VLT, Gemini South, and remote robotic telescopes via the Virtual Telescope project. Scientists at institutions such as NASA's Jet Propulsion Laboratory, JPL, the European Space Agency, ESA, and universities worldwide are combing through the data for signs of unusual isotopic ratios, rare elements, dust grain properties, and outgassing dynamics. Meanwhile, the public is able to watch live via the Virtual Telescope's web TV sessions, and amateurs with moderate telescopes are preparing for observation opportunities in the coming months. What's vital? The cameras, spectrographs, and filters are delivering unprecedented views. We already have detections of a CO2-rich coma, tail lengths of 100,000 km plus, hyperbolic trajectory confirmed, and suggestions of age beyond our solar system comets. And yet, no definitive alien revelations, no proven non-natural origin beyond being interstellar. Scientists are cautious. As a piece in Sky at Night magazine put it, no, our solar system's interstellar visitor is not aliens. Here's the science to prove it. And that's the fascinating tension. Extraordinary object, rigorous science, still many unanswered questions. Audience engagement, what you can do. If you have access to a telescope or plan to visit a dark sky site, you might follow updates on where 3i ATLAS will be in your sky. Astronomical apps, telescopic communities, and platforms like the Virtual Telescope Project live streams can help. Leave a comment below. Do you think we'll detect something truly unusual, e.g., exotic chemistry, unexpected behavior, in this comet? Or will it turn out to be just an extraordinary but natural visitor? And make sure you subscribe and turn on notifications. I'll be releasing follow-up videos as new data comes in, especially after the perihelion date, after which we'll finally see how the object emerges from the sun's influence and what its tail and coma will look like in the outbound leg. What do you think we'll discover next? A fragmentation event? A weird isotopic signature? Or perhaps a surprise entirely outside our predictions? I'm really curious what you think. I read all your comments. Estimated time mark was 10:30 so far. From here we continue deeper into detailed blocks, adding further segments, full investigation, and concluding part. Detailed block, tail growth and coma evolution. In the new images released by the Virtual Telescope Project and partner observatories, the tail of 3i ATLAS shows rapid development. On 27 August 2025, the Gemini South Observatory captured a color image where the tail length measured about 30 arc seconds, some tens of thousands of kilometers. And by mid-September, tail lengths are approaching 50 arc seconds, 100,000 kilometers, according to compiled data. What makes this interesting? For a comet at that distance from the sun, tail formation of that scale is somewhat unexpected because solar heating is lower than for typical comets nearer the sun. Yet here we see quite active behavior. Spectroscopic data show that the coma is rich in carbon dioxide gas and has a significant amount of water ice in the nucleus. But crucially, the lack of substantial carbon monoxide suggests thermal processing in its native environment before ejection from its parent system. Space. In other words, this object may have experienced a warmer environment, or closer to its parent star, than standard solar system comets formed at the outer edge. That's a hint about its origin, and also about how comets behave in different stellar systems. What surprised many people is that tail morphology seemed broader, the dust grain size potentially larger, inferred from the tail's spread, and the dust-to-gas ratio may differ from our typical solar system comets. Observations continue. This leads to the next question. Might this object fragment or outburst as it nears perihelion? It remains to be seen, but this is something astronomers will be watching closely. Detailed block. Chemical and physical composition. Let's dig into the scientific data. According to the JWST and SphereX observations, the CO2 to H2O ratio is unusually high, meaning that relative to water vapor, the carbon dioxide is more abundant than expected. The nucleus size is uncertain because it's obscured by the coma, but estimates place it possibly in the range of a few kilometers across. The coma's angular size in some early images was about 2 arc seconds, full width at half maximum, and extended to 10 arc seconds in some frames. Tail length for dust was around 100,000 kilometers as measured in mid-September. The object's trajectory, inbound from interstellar space, hyperbolic eccentricity, greater than 1, not bound to the sun. Now, what does this imply? It suggests that this object underwent a different formation and thermal history than most solar system comets, likely ejected from its parent star system long ago, traveling through interstellar space, and now experiencing solar heating for the first time within our observation window. In other words, we're not just studying a comet, we're studying a relic from elsewhere. This opens a window into planetary formation in other systems, into the composition of comets from other star systems, and potentially into how volatiles behave under different conditions. Interestingly, that also means predictions are harder, because if we only have solar system comets as a reference, some of the behaviors of 3i Atlas might surprise us, and that's exactly what we're seeing. Let's map the path. The object trajectory takes it from a region outside our solar system, plunging into the inner solar system and making a closest approach to the Sun, perihelion, on 29 of October 2025. It approached from the direction of the constellation Sagittarius, moved through Ophiuchus, Scorpius, Libra as it moved inward. In visualization software, you'd see a steep, highly inclined path relative to the ecliptic, which is atypical for most comets formed in the solar system's Kuiper belt or Oort cloud. The hyperbolic eccentricity confirms it's unbound. So what does that tell us? It means this object won't linger. It is passing through, not captured. It gives us perhaps tens of months of observation at best. After that, it will fade and depart. It also means that targeting it for spacecraft or proximity measurements is extremely difficult. Mission planners estimate that a flyby would have required extraordinarily high delta V if launched after discovery. Thus, these images and data we now have might be our only chance to study this object up close. Updated calculations and stability questions. According to simulations, the outgassing and tail formation suggest high activity levels even at large heliocentric distances. If the dust and gas ejection rates continue rising as perihelion nears, the nucleus might undergo structural stress, possibly fracturing. We've seen this before in comets, but rarely for interstellar ones. Observations suggest that the coma is expanding rapidly, and tail evolution is faster than expected for the distance. The physics: the closer to the Sun, the stronger the solar heating, the more volatiles sublimate, the higher the dust ejection pressure. That's standard. But because 3i Atlas's composition is different, with high CO2 relative to H2O, the reaction may be more vigorous. The stability question: is the nucleus strong enough to resist fragmentation? If it breaks, the tail might suddenly brighten or disperse. Observatories are on alert, and will likely see changes in morphology, coma size, dust production rates. On the instrumentation side, spectrographs will monitor not just dust, but gas emissions, cyanide detection, nickel detection, etc. Early reports suggest nickel and cyanide may have been found. In other words, this story is unfolding, and each new image could show a change. Some things we expected but did not immediately observe. Significant carbon monoxide outgassing, which is common in many comets formed in cold outer regions of solar systems, appears to be low. Instead, CO2 dominates. Space. Also, the tail initially seemed weak relative to some comets undergoing heavy outgassing. That changed later, but the early weak tail raised questions about dust grain size and activity onset. The dense stellar background in the Sagittarius region may have made early observations difficult. What surprised many observers is that the object seems fairly quiet compared with expectations for something newly exposed to solar heating. Yet, tail and coma growth accelerated faster than many similar distance comets. That contradiction is intriguing. Therefore, something about its internal structure, dust grain cohesion, volatile content, thermal history is different. This missing piece will help refine our comet models and our understanding of interstellar visitors. One of the powerful aspects of this event: the coordination between professional and amateur astronomers. The Virtual Telescope Project's livestream enabled amateurs globally to point their small telescopes and help with tracking and tail morphology. Tools such as the Virtual Telescope's Web TV, real-time observation sessions, and citizen science platforms mean that more data arrives faster, tail changes are noticed quickly, and public engagement is high. This event is a reminder that astronomy is not just for the big players. Global collaborators, hobby astronomers, students can make meaningful observations. It also highlights the transparency and access of new astronomical projects. The images released by Virtual Telescope are publicly viewable, allowing worldwide scientists and enthusiasts to inspect, annotate, and integrate data. That helps accelerate understanding, and that's important because the answer still lies in the vastness of the stars. But the more eyes we bring to the sky, the sooner we'll find the clues. While scientists remain cautious, the idea that 3I Atlas might carry material from a vastly different star system raises questions. Could its composition include materials not commonly found in our solar system? Could dust grains from it hold isotopic signatures of another stellar environment? Could the speed and trajectory hint at past gravitational encounters, ejection mechanisms from its original system? Some speculative voices ask, if we learn about one extrasolar comet, what might we learn about planet formation in other systems? And though we must emphasize, there is no credible indication at this time that 3I Atlas is anything but a natural object. As one article put it, not aliens. Still, the possibility of uncommon chemistry or a previously unseen class of comet is very much on the table. And that's part of what makes this so compelling. In a way, this is our chance to peer into another solar system's history through a tiny ice body that happened to wander into our neighborhood. Countdown to key moments. Let's reiterate the key upcoming milestones. 29th of October 2025, perihelion, closest approach to the Sun. Mid-December 2025, closest approach to Earth, though still safe. Between now and then, the observable tail, coma, and dust production may reach peak intensity. After perihelion, the object will begin its outbound leg, fading gradually. What that means, the next few months are a critical observation window. Telescopes worldwide will train on it. Reductions in brightness, changes in tail morphology, fragmentation risk all increase after perihelion. If you're an amateur astronomer or part of a skywatching group, plan your tracking sessions. With sites in the southern hemisphere, Chile, Australia, and northern Hawaii, Arizona, all participating, the global coverage is strong. The countdown to discovery has officially begun. Aside from the awe factor, this matters scientifically because interstellar objects like 3I Atlas offer direct samples, via remote sensing, of material from other star systems without needing a mission launch. They help us test comet formation models under different conditions than the solar system. They challenge and refine our understanding of volatile chemistry, dust grain size and dynamics, tail formation under varying heating regimes. They raise the baseline for surveying future interstellar arrivals, and may help us detect and characterize them earlier next time. In short, we're learning more about our solar system by studying something outside it, and that's an exciting reversal of perspective. Challenges and what we still don't know. Of course, many uncertainties remain. We don't yet know the precise nucleus size because the coma obscures it, the full isotopic or elemental makeup of the dust and ice, whether fragmentation will occur or if the nucleus remains intact. How many other interstellar comets are lurking undetected? How representative 3I Atlas is of interstellar comets, i.e., is it typical or exceptional? In other words, the data is improving, but interpretation is still emerging. The scientific community is cautious because extraordinary claims demand strong evidence, and we're still gathering that evidence. As we watch 3I Atlas cross our skies, we are reminded that the universe is more interconnected than our solar system-centric view sometimes allows. This comet is a visitor, a messenger of material from another time, another place, another star system. Could it be that every few years an object like this passes by and Earth's telescopes are simply not ready to catch it? Perhaps. The more we scan, the more we see. So in the end, what we learn from 3I Atlas may reshape how we think about comets, interstellar matter, and the dynamic environment of our galaxy. The answer still lies in the vastness of the stars. If you want to follow this story as it continues to unfold, make sure you subscribe and turn on notifications for this channel. I'll be releasing follow-up videos as new data comes in, especially after 29 October 2025, when we'll finally see how 3I Atlas behaves at perihelion and beyond. Leave a comment below and let me know. What do you think we'll discover next? Will the nucleus fragment? Will we detect unusual chemistry? Do you think this is just a natural comet and or something weirder? I'm really curious what you think. I read all your comments and would love to know your thoughts. Thanks for watching. Keep looking up because the universe never stops surprising.